Let's talk about today about electrophiles. What is that? So electrophiles. So the name say files is from the Greek word philia. So love electrons. And that is to define species that are actually electron poor. So they're missing electrons somehow. So we think of electrophiles is, say for example, I have this carbocation. Here octet is incomplete. We have a positive formal charge. So again, going by our definition, we're going to say here that electrophiles are electron poor or electron deficient species. That is one example. Because they're deficient in electrons, well, they love electrons, so hence the name electrophiles. Another example of that could be, say, not exactly a formal positive charge, but we can have a dipole here. Say this carbon is attached to chlorine, and so that makes this bond polar. So this is delta positive, this is delta negative. So the carbon there is electrophilic. And because of that, a species like that, electron deficient, can be attacked by an electron-rich species, which are nucleophiles. Now, say another example of electrophile. I can have, say, this molecule. Say that we have acetone here. Well, we know that we have a dipole, and of course, this is going to be delta positive, this is delta negative. But also, we can explain the electrophilicity of the carbonyl carbon by doing resonance. Say that I have this one resonance structure and I can move these electrons over. So the oxygen in my resonance structure will have here a formal negative charge at the oxygen, a formal positive. So here, in two ways we can explain that the carbon here at the carbonyl group is electrophilic. So it can undergo a nucleophilic attack. Let's do one more example of electrophiles. Say that I have now this molecule. And here I have a double bond. This molecule is a ketone, but it is alpha, beta, unsaturated ketone. So let's do resonance here. We know already that the carbonyl here is delta positive, looking at the structure above. But let's do resonance again. So if we do move those electrons over to the oxygen, we're going to create the following resonance structure. Here you will have similar to the one above. So negative charge here, positive here. But now, this here, this charge, positive charge, is allelic, is next to this double bond. So we can do more resonance. We can move these electrons over here. And in doing so, we are creating another resonance structure. And in this resonance structure, now I have a formal positive charge at, say, the beta carbon respect to the carbonyl. In other words, here with resonance, we have demonstrated that the carbonyl carbon and the beta carbon here are electrophilic. And because of that, they can again undergo nucleophilic attacks. So depending on the nucleophile, this type of compounds, some nucleophiles prefer the direct attack over to the carbonyl carbon, and others will attack the beta carbon. That is seen later in more advanced in organic chemistry as a Michael attack. Let's do one more example of electrophile. And here, we just erase this one. Now, let's think of now boron trifluoride, for example. And this color is not helping me much, so I'm going to redraw that. So erase that. Okay, so let's do boron 5 And I'm going to draw the Lewis structure like that. Now we know boron here has the octet is incomplete. You have 6 electrons around. So here, boron trifluoride is a Lewis acid. So as Lewis acids then are electron deficient, octet is incomplete. So Lewis acid can also be electrophiles. And here I'm going to draw a species that is THF, so tetrahydrofuran. We will have electrons here. So that oxygen is electron rich. So we can have, say, an attack over here is a nucleophile, electrophile, but this is also, you can see this. This is Lewis acid, Lewis base, the electron donor. And the resulting, after that, let's see the structure that results complex. Now you will have the octet complete at the board. Let's do that. So after the Lewis acid base reaction, then you will obtain the following structure. Here you will have a formal positive. And now octet is complete at the boron atom. And you will have here a formal negative charge. Remember how to do formal charges. Point is then that Lewis acid are electron deficient species, so they can act as electrophiles as well. And there will be instances in which, for example, another, this compound is also Lewis acid, but it can act as a catalyst. And here is using, we're using the fact that it is electron deficient, octet is incomplete. So here we have seen several examples of a species that are electron deficient, and those we're going to name electrophiles. And here we have been doing also the parallel with electrophile in Lewis acid. We are going to apply those concepts in nucleophiles and electrophiles to organic reactions now.